Alright guys, some of you have asked for a complex ion video just to kind of help you with the rules that we follow when we're predicting these products. First and foremost, don't make complex ions any more complicated than they need to be. There is a lot to them, but we are not going that far in depth with it. A lot of the rules that you're learning here are good baselines, but they're not completely 100% true. There are a lot of things that can affect this, but in terms of us predicting products of complex ions, these are the rules we use, and this is what we'll continue to use in this classroom. When you get into college and start taking some of the upper classes, like inorganic chemistry, and really start understanding coordination complexes, the other term of complex ions, a lot of these rules will make a whole lot more sense and will be elaborated on thoroughly. When we're talking about what a complex ion is, it's some type of transition metal. It can be a regular metal as well, but commonly the transition metal is the one that's going to have this occur, and it ends up with these things surrounding it, and those things are what we call ligands, and those can be ions, those can be compounds. They can be really complex compounds such as DNA, or pieces of DNA, or looking like DNA, nucleic acids, or it could just be something simple as hydroxide or chlorine. How many ligands does depend on the charge of the metal in particular. So let's say the charge of the metal is +2. That means the number of ligands is going to be 4. It's twice the charge of the ligand. Twice the charge of the metal is how many ligands are going to be present in that particular complex ion. Just so we can kind of get an idea what a complex ion looks like, and again, this is a simplified version, but it's just to kind of help us. This in particular would be like an octahedral Lewis structure, if you kind of remember back to that terminology. It's not called the same thing in inorganic chemistry, if I remember correctly, but it may have the same term just because it has similar structure. But let's say this is a nickel ion on here. Well, what happens is we have this attraction between these elements around, our compounds, our ions, or whatever, around the nickel. And basically it almost looks like a covalent structure, or like a polyatomic ion, but it actually is an ion. It's kind of like that polyatomic ion, where it's a covalent compound, but it has a charge. This is kind of like an ionic compound, but it has a charge, but it's not really an ionic compound, because the rules are a little bit different. Hence the reason it's a complex ion. Okay, just so we can kind of see this, let's say we have a concentrated solution of ammonia is added to a solution of copper 2 chloride. The key here is concentrated. There has to be a significant excess of that particular ligand. And again, our 3 ligands are ammonia, chlorine, or hydroxide, are the 3 that we're really looking for here. So we have ammonia here, and we have chlorine here. But we have concentrated ammonia, meaning we have a lot of ammonia. So it's going to be our ligand. Again, oversimplified, but that's the rules we follow. So our transition metal is copper 2. The reason I'm not showing chlorine is because I'm just starting with my net ionic equation. I'm not writing a reaction and getting my net ionic from it. I'm just starting with the net ionic, and chlorine is not part of the reaction, so I remove them entirely. So copper +2 plus my ligand, which again in this case we decided was ammonia because it's the concentrated version, or it's the excess, or what we have a lot of. I then draw my brackets. Remember we used as brackets when we showed like a nitrate ion. When we had this going on, we would have this in brackets with a -1 on the outside. The brackets just shows that what's inside of the bracket has a charge, and the whole thing is combined with a charge present. So that's kind of what the brackets represent. So in brackets we have copper, parentheses, our ligand NH3, and again the number of ligands comes from our charge, which is a +2. And there should be a 4 here because we have 4 ammonias. So Cu parentheses NH3 4, close brackets, and then the charge +2 is coming from the fact that copper is a +2 here, and ammonia is neutral. So +2 plus 0 equals +2. So that's the charge I throw up here. Same thing down here, manganese 3 chloride is added to excess hydroxide ions. Again, we have our chlorine, but we have excess hydroxide, not excess chlorine. So our transition metal is manganese 3, so Mn plus 3. Our ligand is hydroxide, OH minus. We draw our arrow, parentheses, or bracket, sorry, manganese parentheses, OH close parentheses. The number of hydroxide comes from the fact that it's +3, so twice that is 6. And then the overall charge comes from the fact that manganese is +3. We have 6 hydroxides that are -1, so that's -6. So +3 plus -6 equals -3. So again, that's my charge. Practice a couple more of these. We won't do all of them. Let's come down here and look at the last one here. Excess concentrated aqueous ammonia. So that's what we have a lot of, is the ammonia. Is added to a solution of nickel 2 nitrate, leading to the formation of a complex ion. I will always tell you if a complex ion is forming, so that's not something you just have to recognize like you do a single replacement or double replacement. I will tell you that's what's forming, so there's no confusion. So again, the first thing we need to do is pick out our metal and our ligand, and our metal here is nickel 2 nitrate. I'm not going to care about the nitrate. It's not one of our ligands. It can be, but it's not one of the ligands we're going to use. So nickel plus 2 is being added to concentrated excess ammonia. That's my ligand. I have a lot of that, and ammonia is NH3 neutral. I draw my arrow and I start with my bracket. Inside my bracket, I'm going to have Ni, parentheses, NH3. NH3 is my ligand. It's what's surrounding my nickel. How many comes from twice the amount of charge? Well, this is a 2, so I should have 4 nickels. Not 4 nickels, I'm sorry, 4 ammonias. And I'm going to put a 4 over here as well. Now my overall charge of this guy, plus 2 plus 0 equals plus 2. So my charge for the complex ion is a plus 2. Let's grab this one up here as well. Excess hydrochloric acid is added to a solution of cobalt 2 nitrate to produce a coordination complex. Again, same thing as complex ion, so I'm telling you what's going on. Find our transition metal. Well, it's the cobalt plus 2. So CO plus 2 is added to our ligand. Well, I've got chlorine, and that's about it. Again, nitrate could be, but chlorine's our main one. And I have excess of it. Excess, concentrated, a lot of, anything like that's kind of our key word. You're looking for the thing that there is a ton of, and in this case, it's our chlorine. We're not going to do with the hydrogen, because remember, hydrochloric acid is a strong acid, so when it is put into water, it deionizes completely. It's not the hydrogen that's forming the complex ion, it's the chlorine ion. So the hydrogen stays in solution, just like the nitrate did down here. We kind of ignore it. We're just writing the net ionic equation, meaning we don't care about the hydrogen, we care about the chlorine. So Cl minus. And it is forming our complex ion, which is going to be CO. I'm not going to put chlorine in parentheses here because it's just an individual piece. How many, again, is twice the charge. So if cobalt's plus 2 here, I need 4 chlorines, and I close my brackets. So if this is plus 2, and I have 4 chlorines, so 4, negative 1, so negative 4, plus 2 plus negative 4 gives me minus 2. So that's kind of the quick version of complex ions, but again, what you're really looking for is kind of the rules, and that's about it. Hope that helps, guys.